Alright, today we'll be looking at how to graph absolute value functions. Absolute value functions are of the form y is equal to a absolute value x minus h plus k. This will always be the form, and if you don't remember what an absolute value is, absolute value makes a value positive. So for example, absolute value of 4 would be equal to 4, absolute value of negative 4 would also be equal to 4. Alright, so when you evaluate an absolute value, it becomes positive. So, in order to graph this, we will first find the vertex, which is the lowest point or the highest point, and then we'll graph at least two values above or below the x value of the vertex, and then we'll graph. When you're looking at an absolute value function, the x coordinate of the vertex, which is the letter h, will be inside here with the x. And then the y coordinate of the vertex, which we represent with the letter k, will be on the outside of the absolute value. It will be the constant being added to it. So let's see how this actually plays out. When we try to graph it. First, let's look at the parent function. The parent function is the main function, the main absolute value function. All other absolute value functions stem from this function, and it's just y equals absolute value of x. We can pretend that there's a plus 0 in here and a plus 0 out here, which means our vertex would be the ordered pair 0, 0. So our vertex is going to go in the middle of our table. To find the rest of the ordered pairs, we need two x values going this way and two x values going this way from 0. So we need two x values smaller and two x values larger. So we'll do -1 and -2, and then we'll do 1 and 2. So we've got 5 x values here. For each one of them, we need to evaluate the y value. 0, 0 is already done. But for the rest of them, we need to evaluate the y value. So we're going to go back to this equation and plug in each x value to get the corresponding y value. So for y equals absolute value of -2, that would just be 2. So our first ordered pair would be -2, 2, which is right here. And we'll do the same thing for -1. Y equals absolute value of -1, which is 1. So our next ordered pair would be -1, 1. We already have the vertex 0, 0. And next we will do 1. So y equals absolute value of 1, which is 1. And then for the last one, y equals absolute value of 2. Well, let's graph 1, 1. 1, 1 is right here. For the last one, absolute value of 2 is 2. So we'll also graph the ordered pair 2, 2. So you notice it looks like a V. And all of our absolute value functions are going to look like a V. You'll also notice that it is reflected about the vertex. Okay, it looks the same on the left side and the right side of the vertex. Now all of our absolute value functions are going to look pretty much identical to this. Just the vertex will be somewhere else, and it may be skinnier or wider opening this way, and it might open down as well. The domain of this, the domain is all of the x values, remember? So all of the x values would be, we want to know the smallest x value, the largest x value, and it actually encompasses all x value. This thing goes all the way to the left on the x-axis, all the way to the right on the x-axis. So we would say that the domain is all real numbers, and we use this symbol, but this symbol means all real numbers. And this will be the domain of every absolute value function. Every absolute value function has a domain of all real numbers. For the range, however, if we look at the y values, 2, 1, 0, they're going down, 1, 2, but then they start going back up, and you can see this. They're going down, but then it starts going back up. So if we want to encompass all of the y values, then the y values are everything above 0. 0, 1, 2, 3, 4, 5. The y values never go below 0. So we would say the range is all the y values greater than or equal to 0. Y could be 0, or y could be anything greater than 0. And you can see that. So the range is usually going to be everything larger than the y-coordinate of the vertex if it's pointing up, or everything smaller than the y-coordinate of the vertex if it's pointing down. So that's the absolute value parent function. All of our other functions are going to look something like this, just in a different place. Now let's look at how we would apply transformations to go from the parent function to a new function. And what we're going to see here is that if there's a number inside of the parentheses with the x, such as this h is going to move it. It's going to move the parent function horizontally. It'll either move it left or right. And then k, the k value, if there's any value added onto the outside of this, that's going to shift it vertically, up or down. And if there is a number that is in front of the absolute value portion, the a value, if that a value, the absolute value of it, is greater than 1, then the graph is going to be stretched vertically. So it's going to be thinner. And if it's between 0 and 1, then that graph is going to be compressed. It's going to be flattened. It's going to be wider. And if that a is a negative value, that means the graph opens downwards. It reflects over the x-axis and it looks like this. And we can see each of these transformations in action when we look at something that has them. Alright, so remember, let's try this. Let's try to graph it using the table and then see if we can tell which transformations have occurred from the parent function to this new function. So remember, the vertex is h comma k. So h in this case is 2. Remember, because it was, if we know the equation of the parent function, it's y equals a x minus h plus k. So in this case, h would be 2, because minus 2 minus h, so h is 2. If this was a plus, then the h would be negative 2. So the vertex has an x-coordinate of 2 and a y-coordinate of 4. So let's put that on our table. Alright, now we're going to want to evaluate, well, first of all, let's do our table. We need 2 points that are smaller, so we'll go backwards, 1, 0, and we'll do 2 points that are larger, 3, and 4. And we're going to want to evaluate the y-coordinate for each of these x-coordinates. So we'll go ahead and plug them in one by one. So we'll start with 0. Y is equal to negative absolute value, 0 minus 2 plus 4. Alright, so that's negative absolute value of negative 2 plus 4, which is negative. Absolute value of negative 2 is just positive 2. But remember, this negative sign is still here, plus 4. And then negative 2 plus 4 is 2. So our first ordered pair on our table is 0, 2. Alright, let's do this with the next one. I really thought that would erase it. This is kind of a pain. Is there a larger one? There we go. There we go. Alright. Let's try it with 1. So we're going to do y is equal to negative 1 minus 2 plus 4. So that would be negative 1 minus, absolute value of 1 minus 2 is negative 1, and then plus 4. So that would be negative, absolute value of negative 1 is 1, plus 4, which is 3. So our next ordered pair is going to be 1, 3. Alright, so we're just going to go through these and plug them all in. And it looks like I've erased a little bit more than I meant to. So after we plug them in, we plug in 3, we will get 3, and we plug in 4, we will get 2. And you can go back and check these if you like to make sure that I am correct. So what I'm going to do is I'm going to graph these. So 0, 0, 2, I will graph first. Just going to graph these in order, and I should get an absolute value function 0, 2, and then 1, 3, and then 2, 4, and then 3, 3, and then 4, 2. And we can see we have our absolute value function looks like this. Alright. Our domain is all real numbers, and our range is everything below the vertex, which is 4. So y is everything less than or equal to 4. But if you notice the transformations that have occurred here based on the h and the k values, because this is the graph, but remember what the parent function looks like. The parent function starts at 0, 0 and goes up like this. So what's actually happened here is it has been shifted, from the parent function. It's been moved to the right by 2, it's been moved up by 4, so right by 2, up by 4, but it's also been flipped upside down because of this negative sign here. So even though we have the table here, we could have known how this looked based on the transformations. Right by 2, moved over by 2, and moved up by 4 from here to here, from our parent function to our new function. And this negative sign turned it upside down, because remember, if the a is negative, flips upside down. And that is it.